Good day, everyone. We are group number 5 and we are here for our problem presentation number 3. So for our first problem involving a simple linear regression, an article in the Journal of the Environmental Engineering Division took a sample from the Holston River below Kingport, Tennessee during August 1977. The biochemical oxygen demand or BOD test is conducted over a period of time in days. The resulting data is as follows. Assuming that a simple linear regression model is appropriate, fit the regression model relating BODY to the time x and what is the estimate of the variance? What is the estimate of the expected BOD level when the time is 15 days? What change in mean BOD is expected when the time changes by 3 days? Calculate the fitted y for each value of x used to fit the model. Then construct a graph of y versus the corresponding observed values y and comment on what this plot would look like if the relationship between y and x was deterministic or no random error, a straight line. Does the plot actually obtained indicate that time is an effective regressor variable in predicting the BOD? So for the first step would be determining the slope. In determining the slope, the equation used is as follows. Dsxy over sxx, which would give us a value of 0.17806 for the value of beta 1. For the second value, beta O, or the intercept, we could use the formula beta O is equals to the mean of y minus beta 1 mean of x. This would give us a beta O value of 0.65776. And combining these values taken, we can now produce an equation of the linear regression equation y equals 0.65776 plus 0.17806x. Now in getting the variance, we use the equation sum of squares error over n minus 2. Since SSE is still unknown, we get SSE from SST minus beta 1 SXY. And SST would be taken from the summation of y minus the mean of y squared, which equates to around 14.08. Then plugging in those values would give us a some square error of 0.74248, and plugging that value into the equation would give us a variance of 0.08250. Now, when x is equal to 15, we just need to plug in the values. Plugging in the value would give us a y value of 3.32866, which is the biological oxygen demand in milligrams per liter. So getting the change in 3 days we would substitute x is equals to 3, 6, and 9 to our linear regression model or equation. So plugging us the values would give us these y values or the biological oxygen demand, and subtracting them would give us a change in the mean BOD for every 3 days. So the value of the change in mean BOD for every 3 days would be 0.53418 of biological oxygen demand in milligrams per liter. Now, comparing the actual and the predicted values, we give the following residuals per observation. Plotting in the residual plot and the fit plot would give us this. If the relationship were completely deterministic, the residual plot will all be zero. Similarly, the line fit plot would be perfectly linear. Furthermore, to determine if time is an effective regressor for predicting the BOD, we must calculate their coefficient of determination, or R squared, the R squared value. So to get the r-squared value, we would need to use this equation. And using this equation would give us a value of 0.94727. Therefore, the model accounts for 94.727% of the variability in the data, making time a very good predictor of the BOD. Here is the summary of the problem using the Microsoft Excel data analysis tool. So for our next problem, which is a multiple linear regression problem, an article in the IEEE Transactions on Instrumentation and Measurement reported on a study that had analyzed powdered mixtures of coal and limestone for permittivity. The errors in the density measurement was the response. The data are reported in the following table. So fit a multiple linear regression model to these data with the density as the response. Estimate the variance and the standard errors of the regression coefficients. Use the model to predict the density when the dielectric constant is 2.5 and the loss factor is 0.03. Now, to get a multiple linear regression model with using this data, we would follow the least squares normal equation. So therefore, we would follow this set of equations to get the value of beta 0, beta 1, and beta 2. And here is a summary of the values needed for calculating the betas and their summation. Logging in the values would give us these three equations. 10.76 is equals to 11 beta 0 plus 27.64 beta 1 plus 0.326 beta 2, and so on. Now, using a calculator or a Microsoft Excel, you would get the values of beta 0, beta 1, beta 2 using the simultaneous beta solver. So, using that, we would get beta 0 with negative 0.1105, beta 1 with 0.4072, and beta 2 with 2.1080. And using the general formula for the multiple regression model, we plug in the obtained beta values. Then we could get y is equals to negative 1105 plus 0.4072 x sub 1 plus 2.1020 x sub 2. Now, in estimating the variance, we would use this equation. And getting SSE, or the sum of squares residual values, would get us 0.0006, and Vn minus p is equals to 8. Therefore, subbing in and dividing it would give us a variance of 0.000078043. Now, predict the density when the dielectric constant is 2.5 and the loss factor is 0.03. We just need to plug in the values, where x sub 1 is the dielectric constant and x sub 2 is the loss factor. So subbing in those values to the equation we got earlier would give us y is equals to 0.97056. Therefore, we can predict that the error in the density measurement is 0.97056 when the dielectric constant is 2.5 and the loss factor is 0.03, provided that the multiple linear regression model is correct. So here's a summary of the Excel output data analysis for this problem. And that would be all for our problem. Thank you.